This is the lesson video for 4.2 Day 1, Implicit Differentiation. Implicit differentiation calculates a derivative, and it's often used for things that have more than one variable. So while we've done derivatives for plenty of functions, equations that you can solve for y equals, many equations you can't, the example of the circle here, and then more complicated ones. And so we need a method to differentiate, get things like velocity and acceleration for curves that aren't functions. So one approach is that we're going to find the derivative of the equations without having to solve for y equals. If you took the circle example that's here and solved it for y equals, we'd end up with two functions. We'd end up with y equals plus or minus the square root of 25 minus x squared. And instead of doing that, implicit differentiation says that we can handle this. We're going to be deriving with respect to x still, meaning that when we do our derivatives, that's the derivative that we're using. We're using the x derivatives. So as I go through and work on this one, I need to take the derivative of the x squared plus y squared equals 25 function. So when I start doing that, I know how to take the derivative of the x squared part with respect to x, that's 2x. But the y squared part with respect to x is going to be the challenge because y squared isn't in terms of x. So we want to think of this like chain rule. It's some function squared, so its derivative would be twice that embedded function, the y function, times whatever the y function's derivative is. So your notation in your derivative is going to be 2x for the first term, 2 times y times dy dx, and the other side of the equation also has its derivative taken, and we get 0. So we're taking the derivative of both sides of the equation. So in this little part in here, you want to think about chain rule. The goal then is to get the dy dx alone, because dy dx itself represents the derivative in terms of x of the entire equation. So I can get this term alone by moving the 2x to the other side as negative. And then to get that dy dx alone, in other words, the original derivative I was seeking, I'll have to divide both sides by that 2y term. That should be an x. And when I simplify this, we're saying that the derivative of this function is the opposite of the x over its y value. With that derivative, then, I can calculate slope at 3, 4. So the slope at 3, 4 is going to be evaluating that derivative at the ordered pair 3, 4, which means 3 goes in for x, 4 goes in for y, so the value of that derivative, or the slope of the tangent at 3, 4, so adding that point to the picture, is about negative 3/4. So if I was doing that, I'd go down about 3 and over about 4. And that's describing the slope of the tangent to the curve, or the instantaneous velocity at that particular location. This page is a good page to stop the video and take down notes. Implicit differentiation steps are here. Then we'll go through and practice with some. So stop the video here, get the steps written down, and then come back ready to practice on the next pages. So you're back. One thing to add to this page is some people always say, well, what do I do with my y terms? It's still really weird to me. So we saw this in the first one, we'll see it again. But any y terms that you have, or any other variables that aren't the variable you're doing your differential or your derivative with respect to, think about chain rule. For example, we just saw that y squared, when we want to derive it with respect to x, and we want its derivative, that we're going to use chain rule. Twice, don't change the function, take it down a power, multiply by the derivative with respect to x of that function. So every y term is going to end up having a dy dx with it. So in this cubic you've never seen before, likely never seen before. It's kind of a cool cubic. And they would like to know for this particular curve, what's the slope at negative 2, 2? And just looking at it, I'm going to guess it's around 0, but hard to know. And without the graph of it, we wouldn't know that at all. So we're going to do this implicit differentiation idea. We're going to get the derivative of both sides with respect to x. So on this side, we've already seen what's got to happen. So twice the y function with whatever the y function's derivative is with respect to x on this side. Over here, we have all x's, so happy place. So therefore, if I want to get dy dx alone, I'm going to have, in other words, the derivative of the entire equation with respect to x. I'm going to have to divide by that 2y term. All over 2y. There's my derivative. With respect to x, it's all set up, but I'm going to need to know my locations in terms of xy. So they would like to know my slope at xy, so I'm going to be evaluating the derivative at the ordered pair -2, 2. Plugging that into the equation and stop and do the math and all that, you end up getting 12 minus 12 over 4, which is 0. So the slope of that of the tangent at that point would be 0, 0. The next part down wants us to find the equation for the tangent to the curve when x is -1. When I come to the graph, I see that when x is -1, it looks like there's two different points on the curve, and therefore I'd have to get a tangent equation for two different tangents. So as we go through this, stop the video, go back and think about it if you need to. So first thing is we need to find those ordered pairs. I know that they're at -1, comma something, but we need the other part. We need the y value assigned, so we need to go back to that y squared equals the equation of the actual curve. Slide up a little bit so you can see it. To get the values for that, we need to come back to here. So here's what we know. We know that y squared is, and then plugging in -1 and cubing it, plus 3 times -1 squared. We get that y squared is 2, so the missing y values when x is -1 are plus and minus square root of 2, around 1.4. Seems pretty reasonable. So we need to get the points first, and that just comes from the actual equation. No calculus yet. Now to get the slope so that we can actually write the equation for the tangents, we need the derivative. So to find our slopes, we're going to be doing this differentiation process, taking that function and doing its derivative. And you can say, well, we already have it. We do. We have it up above, so we're not going to rederive. We already have the derivative. It's right here. So we're going to evaluate that derivative for each ordered pair. So here's where you might want to stop the video and actually evaluate that for -1 square root of 2, the dy dx. And also evaluate that slope, the dy dx, at the ordered pair -1, negative square root of 2. When you do, and you simplify and you do all the square root work and everything for what you should have, and please stop the video and do that so that you're certain that you can, you end up with slopes that are opposite each other. And then we can go write the tangent equations because we have the ordered pairs and we have the slopes that go with them. So for the ordered pair -1, positive square root of 2, there's my slope. So our tangent equation, y minus square root of 2 is negative 3 square roots of 2 over 4 times the quantity x minus 1. And for the other one, it's going to be y plus square root of 2. For this one, equals, it has positive slope. And that should be an x plus 1. And there are two tangent equations. So here's a chance for you to stop the video, try a few of these, and then come back to the video and see what you've got. So pause now, try a couple of these, and come back only to check them. You're back. All right, differentiating this side's a 1. Differentiating this side, we need to think chain rule. The derivative of the sine function itself is cosine of y, but then we need to add in y's derivative. Getting dy dx by itself, meaning the derivative of the entire equation, is going to be 1 divided by cosine of y, or you could rewrite this as secant y. This one we're going to have to be a little bit slower about. Takes a few more steps. This side will need product rule. This side will definitely need some chain rule. So derivative on this side would be a 1 plus, again, if it helps to rewrite this as cosine of y quantity squared so that you see the chain rule, it would be 2 cosine y, and then chain rule negative sine y, and then after that you have to think about the fact that y is still not something whose derivative we know, so we need dy dx for that last embedded function. On the other side, we need to think about product rule a little bit. So again, whichever order you choose to do this in, derivative of the first times the second plus derivative of the second times the first. That you're going to come back to a lot, so you might want to highlight that one and come back to it a lot in homework. So gather all your dy dx terms on one side. This is a whole dy dx term. I'm going to bring that one over so I can gather them on the same side and factor that dy dx out. So I'm going to keep the -2 cosine y sine y on this side with its dy dx. I'm going to bring over that x dy dx term. I'm going to keep the y on this side and subtract the 1 from over here so that that's on the other side. Pulling out that dy dx by factoring. Again, -2 cosine y sine y minus x, still y minus 1. So my entire derivative when I divide so that I get both sides all set, dy dx alone on one side. And there's one form of the derivative. If you moved your items over to the other side, you could end up with the opposite of the top and the opposite of the bottom. It just depends on which side you gather your dy dx terms on. And either form's okay. Last one. So on this last one, on this side, I've just got single terms that do not require anything fancy. On this side, though, I'm going to think about product rule. I'm going to keep my 3 as a separate value, as a multiplier. Then I'm going to look back to where I did, or redo, that derivative of just the xy term. So on this side, with respect to x, 3x squared plus, you can do this with respect to y at first, but then chain rule says multiply by y's derivative. On this side, derivative, I'm going to think about derivative by product rule. Okay, 1 times y. Again, stop the video, slow it down, do the things you need to do so that you can feel comfortable with that. That's just going back to product rule. So I want to gather all my dy dx terms on one side after I distribute. So I'm going to end up with 3y squared dy dx. On this side, after that 3 distributes, I'd have a 3x dy dx. So I'm going to bring that over. And take as many steps of algebra to do this as you need. On this side, I'd still have a 3y, and I'd bring over the minus 3x squared in order to get those terms that don't have a dy dx over there. Factor out the dy dx so that I can divide both sides and get an expression that demonstrates what the derivative should be. All of these I notice have a factor of 3 in them. So if I factor a factor of 3 out of the numerator and a factor of 3 out of the denominator, and yes, we should simplify enough to see that. So our derivative, y minus x squared over y squared minus x. If you moved everything to the opposite sides, then yours could be, and it would be fine, x squared minus y over x minus y squared. Either form of the derivative would be fine. Have a good one, folks.